Welcome to today's Explainer. I'm so glad you're here. We're diving straight into something that sits right at the heart of modern engineering. It's often brushed off as just a tedious software chore, but we're talking about meshing in finite element analysis, or FEA. And honestly, creating a mesh isn't just some mathematical necessity. It is this incredibly elegant balance of art and science. It takes real intuition, precision, and a deep understanding of how physical objects actually behave under pressure. But before we get too swept away, let's establish the golden rule here. Garbage in, garbage out. It is so tempting, isn't it? You look at this beautifully rendered, brightly colored 3D model on your screen, and you just want to believe it represents absolute reality. But here's the catch. A colorful stress contour means absolutely nothing if the underlying mathematical mesh is flawed. If your foundation is off, those pretty pictures are, well, just pretty pictures. They don't represent reality at all. So, here is our roadmap for today's explainer. First, the foundation of FEA. Second, element types and quality. Third, the Convergence balancing act. Fourth, navigating stress singularities. And finally, number 5, we'll look beyond traditional meshing. All right, let's start with section 1, the foundation of FEA. To really appreciate the art of the mesh, we've got to look under the hood. Imagine you have a continuous, highly complex physical object. Let's say an engine block or an aircraft wing. Mathematically, it's just way too complex to solve all at once. So what do? Well, we transform this continuous object into a giant puzzle made of discrete mathematical pieces. This network of elements and nodes breaks that continuum down into much smaller, manageable equations that a computer can actually solve. Now, here is the really crucial part. FEA relies entirely on discretized calculations. What does that mean? It means the computer is only calculating equations at very specific points, which we call nodes. For all the empty space inside the element itself, the values are just guessed or interpolated based on the element's specific mathematical shape function. Because we're only calculating at these specific points and interpolating the rest, the shape of the puzzle piece, our element, is absolutely critical to finding the truth. Moving on to section 2. Element types and quality. So what exactly makes one of these little mathematical puzzle pieces good or bad? Well, we need to talk about the primary villains of element quality. These are the silent corruptors of your data. First up, Jacobian distortion. This is when elements are severely twisted away from their natural ideal shapes. Then we have high skewness. This deviation from perfect symmetry causes totally non-physical, uneven stress interpolations. And finally, poor aspect ratios. These are thin, completely stretched out elements that can severely compromise the mathematical stability of the entire solver. And this shows you exactly what happens when those villains infiltrate your model. Modern FEA software is actually incredibly smart. It actively hunts down these shape violations. Take a look at those little X marks in the Nastran output file. That's essentially the software elegantly sounding the alarm, pointing out exactly where your elements have violated the acceptable tolerance limits for skewness and aspect ratio. But element quality isn't just about the physical shape, it's also about formulation. Analysts face a bit of a Goldilocks dilemma here. If you go with first-order, reduced integration elements, your model might suffer from something called hourglassing. It's a zero-strain deformation mode that makes the element entirely too flexible, kind of like a wet noodle. But if you try to fix that by using fully integrated elements, you risk shear locking, where artificial shear strains make the element way stiffer than reality. You really have to find the element formulation that is just right. So why does all this matter so much for your actual projects? Well, consider a really simple cantilever beam test from our sources. Traditional hand calculations tell us the true deflection is exactly 2.000 millimeters. But just by choosing the wrong element formulations, falling into those traps of hourglassing or shear locking we just talked about, analysts got predictions ranging from roughly 1.3 all the way to 2.6 millimeters. That is literally double the deflection. Just imagine 2 analysts working on your project, making critical, expensive design decisions, and getting wildly different results just because of the element they chose. Which brings us to section 3, the Convergence balancing act. You see, even if you select the absolute perfect element formulation, the physical size of those elements plays a massive role. To get to the truth, analysts undertake a systematic journey called the mesh convergence study. You start with a coarse, simple mesh just to get a baseline. Then you step-by-step refine that mesh, making the elements smaller, but only locally in the hot regions where stress is really concentrated. You plot these outcomes against the element size, and eventually you'll see a point where the results asymptotically level off. Right there, that's your just right density, where the numerical errors finally fade away. Now, throughout this study, you are walking a real tightrope between two extremes. On one side, you have the coarse mesh. Yes, it's incredibly fast to compute, but it's full of massive, dangerous errors. On the other side, you have a uniformly fine mesh across the entire model. Now, while that might sound perfectly accurate, it's actually a trap. It will eat up an enormous, totally unnecessary amount of your computational time and memory. So how do we speed things up without compromising the data? We rely on a really beautiful piece of physics called St. Venant's principle. This principle essentially tells us that local stresses in one region don't deeply affect the stresses far away from them. This is huge because it allows analysts to smartly refine the mesh into tiny elements only in those critical high stress areas, while safely using much larger, computationally cheaper elements everywhere else. It literally saves hours of computing time while keeping the fidelity incredibly high. And honestly, when this is done properly, the results are just deeply satisfying. The sources detail this wonderful real-world example of a 3D crane hook loaded with 70 kilonewtons of force. By doing a rigorous mesh convergence study and using the right element sizes, the simulation gave a maximum stress that was incredibly close to the classical analytical hand calculations. We're talking a difference of just 1.1%. Now that is the power of a perfectly converged mesh. Now let's step into Section 4, Navigating Stress Singularities. Okay, it's time to talk about the hidden monsters lurking inside FEA models. A stress singularity is essentially an analytical anomaly. It's totally different from a normal stress concentration, which eventually levels off as you refine your mesh. A singularity is a spot where the mathematical stress infinitely increases the smaller you make your elements. They absolutely love to hide in perfectly sharp inside corners or anywhere a load is applied to a single infinitely small point. And it is just a completely frustrating reality for any analyst. As the quote from our sources highlights, no matter how much you refine mesh, there will be higher and higher stress all the time. It's quite a paradox. You think you're doing the right thing by making the mesh smaller and smaller to find the truth, but instead the math completely breaks down and the fake stress just gets worse and worse. So what exactly is in an engineer's toolkit to handle these anomalies? Let's look at the options neutrally. You could just ignore it, citing St. Venant's principle, but that's really risky because some legitimate stress does exist there. You could model a tiny radius or fillet, though realistically that's often a geometric utopia and computationally very heavy. A much more practical, low-risk solution is to apply the load over a realistic physical area instead of a single mathematical point. Or, and this is quite elegant, you can use a nonlinear material model. This naturally caps the infinite stress by allowing the material to locally yield. Finally, Section 5, Beyond Traditional Meshing. After spending all this time detailing the careful art of creating the perfect grid, I actually want to ask you a rather challenging question. What if we could simulate highly complex physics without connecting nodes into a mesh at all? Well, this is the brilliant promise of mesh-free methods. Techniques like smoothed particle hydrodynamics, or SPH, literally liberate the data points from a rigid grid. Instead, they treat nodes as individual physical particles that carry mass and can move around freely. Because there's no mesh to get tangled up or distorted, it perfectly handles massive, chaotic deformations. It's absolutely ideal for fluid dynamics or simulating severe cracking. And here is a really fun fact from our sources. This is exactly the method the movie industry used to simulate that beautiful, highly realistic snow in the movie Frozen. Which really leaves us with a final, somewhat provocative thought. As our computational power grows exponentially, will the meticulous, delicate art of finding the perfect finite element mesh eventually be rendered obsolete by the raw, untethered power of mesh-free particles? It is such a thrilling time to be involved in engineering simulation. I really hope this explainer has empowered you with a deeper understanding of the mesh and inspired you to look a little closer at the science beneath the pretty pictures. Thank you so much for joining me today.